I should be set any moment. Yes, here I'm set. Okay, yes, thank you. So much once again for inviting me for this talk. As the title of my talk states, so I'll speak about specifically physics and the mechanics of slip-on faults, all across the different length scales we can actually study it in, and with a particular stress on how specific types of standard laboratory experiments can actually be used to understand yes.
Every 2-3 seconds, your voice is being muted. I mean, is it due to internet trouble or so, or what? I am Professor Anupam Chattopadhyay speaking from Delhi.
I mean,
we can hardly hear you. Every 2-3 seconds, the voice is
okay, Pathikrit, just let me pitch in here. Professor Chattopadhyay and others, so Pathikrit has a little bit speech problem. I request everyone to just so you may hear it in a different way, but So
no, Shantanu. Yeah, Shantanu, it's not the speech problem. He's completely, the voice is coming and going. It is not because of stammering or anything.
No, it's not. I mean, it's not stammering, but I think Pathikrit can manage it. Okay.
So, Pathikrit, please go ahead. I think there is some trouble in the sound system or something.
Yeah, maybe it's echoing. Yeah.
Okay.
But Pathikrit, go ahead. Pathikrit, go ahead.
Yeah. Okay. Fine.
Okay. So no problem. Please.
No, yeah. So I'm absolutely fine. Yeah. Thanks. I mean, in case I start to become inaudible again, I'm please let me once again. Okay.
Yeah. Sure.
Okay.
Sure. Please,
fine.
Yeah.
Okay. Right. And so the specifically stress of my talk would be on trying to understand that how small scale laboratory experiments, which are standardly done on small centimeter scale samples of rocks, can actually be used to understand how crustal scale faults like deform, right? So I'll start off with stage setting example, right? I mean, so it's standard knowledge that on every major plate margin around the world, that strain accumulated in the interseismic period gets released in the form of earthquakes, right? But over the span of the last like 15 years or so now, what we have actually started to understand with improved instrumentation across these plate boundaries is that in fact the strain energy accumulated at these plate interfaces can be released across a spectrum of styles of slip events, right? I mean, which essentially so each of these classes of strain release events have their own characteristic duration, so which can span from a few tenths of seconds all the way to days, weeks, and months. And what's also interesting about this spectrum of events is that on being plotted on a plot like this, where on the x-axis you have actually the log of the scalar seismic moment, and on actually the y-axis you have the log of the event span or duration. The standard earthquakes plot in the small duration high moment spot or slot, while these extremely slow earthquakes can also actually have a significant amount of strain energy release, while occurring across a time scale of days, weeks to months. Now, the most in terms of the spatial location of this aseismic or slow events and the seismogenic or these standard earthquakes. So on a cartoon of a slab like this, just slightly down dip of the trench on a subducting slab, you would have these seismogenic events, while even more down dip from this seismogenic locked patch, you would ordinarily find these aseismic or slow slip events, right? So one important question to ask at this juncture is that like why we should at all like care about these aseismic events, because of course by the virtue of occurring extremely slowly, I mean, they won't cause any damage destruction, right? So the important thing to understand in this cartoon, though, is that as these aseismic events also occur on the same slab as the seismic events, anytime you have any kind of a creep motion on the down dip extent of the slab, that can impact the strain accumulation in the seismogenic zone. So in spite of the fact that these aseismic events on their own are not at all like damaging, they can strongly modulate the strain accumulation on the megathrust part of the plate boundary, and can hence also impacted the earthquake cycle on subducting plate margins. Now, an extremely simple sort of like first order approximation to understand essentially the mechanics of this thing is to imagine that that in the blue you have the subducting slab, and then the whole spatial region inside the slab close to the locked and plate boundary can be is continually accumulating strain as the plate boundary remains locked, and the slab continues to creep beyond the brittle ductile transition, right? So this this part of the slab can only actually accumulate strain specifically due to one reason, and that specific reason is that this interface in between the plates is to some extent frictionally locked, right? So as the strain keeps on accumulating, elastical stresses on the plate interface will also keep on growing, and then when this stress can ultimately exceed the strength, this plate interface can actually start to slip. Now, this elastical strain accumulation in the subducting plate can, in terms of a first order approximation, be approximated as a standard linear elastic spring. So with this approximation, the stress increase in the locked region of the subducting slab can be approximated as some stiffness K times the difference in between the motion of the load point, which in our case will be trying to move at approximately the plate rate. So it's this load point movement and the actual slip of the fault, right? So anytime this stress can exceed the strength, you'll have slip on the interface, and the fault and the region around the fault will undergo a stress drop. And for standard earthquakes, these stress drops are approximately of the order of 100 to 10 MPa, and each time you have a stress drop like this, the fault for standard earthquakes will actually slip extremely fast, and the amount of acceleration in the slip can be of the order of 10 to the power 6 meters per second also. Now, so in terms of the property of the bulk that we need to actually understand this, we have already approximated the strain accumulation in the bulk as essentially a standard linear elastic spring. Yes, but the important thing which we haven't yet determined is that how does actually the strength of the interface in between the two plates actually change. Now, now all our understanding of how the strength of the interface actually does change comes almost entirely from the laboratory, since to make actual observations on such plate margins is extremely difficult. So a standard laboratory setup which can actually be used to study such a thing is shown here on the left. So so I'm sure that a substantial fraction of you will immediately recognize this as a biaxial apparatus. So this specific like design is from the USGS crustal mechanics laboratory. So the important part of the assembly is this like setup of 3 samples of the specific rock type you want to study. So a horizontal and normal stress is imposed on the sample assembly through this horizontal ram, and vertical and normal stress is simultaneously applied through this hydraulic ram from the top. And so this sample in the center can then slide through this the 2 side blocks. And in all of these experiments, what you'll always actually see is a plot of the shear stress as either either a function of time or of slip. So the stress is measured through a standardized load cell on the top and on the bottom here, and a standard transducer is coupled to the fault surface to directly observe slip. So so in experiments like this, if the experimental apparatus is compliant enough, then these stick slip cycles are actually also seen. I mean, so you have these stress drops occurring on the interface of the central little block with the 2 side blocks as this central block is actually driven at a constant rate. And each time you have these stress drop events, you have a large amount of like slip also on the slip interface. Now I am like showing you the same picture of one specific like stress drop, but please note that on the time axis I have now zoomed into the scale of like milliseconds. So what on the plot before seemed like an abrupt stress drop will actually now seem to have a specific finite time duration. So this like curve in the cyan is specifically the shear stress in here. Now in the same sample assembly, what you also had was this laser Doppler vibrometer, which can give like recordings of the fault like slip rate at extremely high time resolutions, and so specifically from the vibrometer, what you can see that the speed of slip of the block does continuously speed up or accelerate all the way from submicron slip rates here to an inertially capped peak here, and then all the way like down and like back to the pre stick slip sliding speed. So the important point to make out from this is that at the initiation of slip, right, the fault was actually sliding extremely slowly and continues to speed up, right? So this entire increase in the slip rate, where actually the fault has started to slide at speeds that are like larger than the loading rate, but still yes, but still orders of magnitude like slower than the peak slip rate, where the substantial part of the seismic radiation actually takes place. I mean, so all of this increase in the slip rate, which happens like right at this early part of the acceleration, is in fact your aseismic slip. Specifically in the sense that the speed of slip is still substantially slower than the speeds at which essentially the fault would have to like slip in order for it to like generate seismic waves. Now, the one more interesting observation about all of this is that in case you carried out the exact same experiment and you once again dragged essentially a sliding block with a spring at a constant rate, like subject to an ambient normal stress, then as you change the level of the ambient normal stress, the style of stress drop in these events in the laboratory can start to actually change extremely drastically. In fact, as you go down in the normal stress, you see that how instead of extremely sharp rapid drops of the shear stress shown here in black, the style of the events increasingly become characterized by much smaller stress drops, and the speeds you have the fault sliding at in these specific slip events comes all the way down from a few centimeters per second at the high normal stress levels to a few hundred microns per second at the smaller normal stress values. So in terms of an observation, this is specifically a point where I would ask you to just stop and think with me for a bit. So in these experiments, what did we have? An extremely simple setup which only had the two samples of the rocks, a spring, right, and just completely dry friction on the sliding interface. And in spite of this extremely simple components of the physics problem, right? What you can already see that just by changing the ambient and normal stress levels, you can transition all the way from seismic slip to aseismic slip. Now, in terms of how you would transition from a higher normal stress to a smaller normal stress on the slab, even though aseismic slip, as I showed you in the earlier plot, is expected to be deeper on the slab. Think fluids, right? So along each important plate boundary across the world, I mean, it is common knowledge that in specifically the zones of high strain localization, one would expect to see large pore fluid overpressures, and so the ambient normal stress in these experiments will only need to be replaced by the effective normal stress, which is of course your ambient normal stress minus a constant times the pore pressure for standard for for standard crystalline rocks, I mean, this constant L comes out to be around 1. Right. So on the top of this aseismic to seismic spectrum of slip events, what plate boundaries around the world also actually show that the same spatial locations on a fault can actually fail again and again. So as an example, on the left, I have a map of small repeating events on the Calaveras strand on the of the San Andreas fault, and on the right, what I have is the stress drop for the smallest of the repeaters. I mean, so all of these repeating earthquakes are approximately of magnitude of 1.5 or so. So the interesting observation from this is that the stress drops which are seen for the same exactly magnitude earthquake keep on continually increasing as a function of the earthquake, the earthquake recurrence interval. So what this picture essentially shows is that in general faults do strengthen as a function of specifically the time in between successive earthquakes. So then any specific friction law which has any hope whatsoever to explain the observed phenomenology of fault slip, we should then essentially be able to predict a mechanism through which one single fault can give rise to both aseismic as well as seismic failure, and then in the interseismic periods, the sliding interfaces should actually be able to strengthen with time, and then on the same sliding interface with changes in the geological conditions, the style of slip should be able to like transition from aseismic to seismic or the other way. Now, in the rest of the talk, what we'll essentially do is specifically look at some candidates for this appropriate constitutive law for sliding friction on faults. So a standard approximation we will actually make in trying to understand these experiments is that will explicitly approximate the applied electric shear stress to be instantaneously equal to the shear strength. This is called the quasi-static approximation. So, and of course, as before, we will imagine actually a spring block slider. So all of the elasticity of the sample plus the testing frame will be like coded into one single scalar stiffness and the speeds of the low point, and the fault will be separately kept like track of. Now, once we start off with these experiments, I mean the absolutely first thing which visually attracts you is the rate dependence of the friction coefficient. So in this specific experiment, what has actually been done is the block has been subjected to a sequence of large steps in the sliding rate. So on the top panel, you can see that the slip rate of the block has been changed in a step-like fashion from starting from 1 microns per second all the way up to like 10 microns per second, and then 1 second, and back to 1 microns, and then like up to a 100 microns per second, and then 1 second back. Now each time you impose a step in the sliding rate of the block, what you can observe is that the friction coefficient instantaneously goes up in value. Yes, but in spite of the fact that the sliding rate of the block is kept like constant across this whole time period, your sliding frictional coefficient is not actually a constant anymore here. See, I mean, so it keeps on evolving like back to a steady state. And then for a step down in the sliding rate, the coefficient goes down, and then it does exactly the same thing actually on the way up as well. So so to explain phenomenologically why something like this can be happening. I mean, one standard way is to start off with the assumption that, well, the friction coefficient mu has an inherent rate dependence in terms of the slip rate of the fault, but then since the friction also keeps on changing even when the slip rate of the fault is actually held constant. Hence, this should have an inherent dependence on at least on at least like one other variable, and so this is called the state variable. Now, to specifically understand what this means, I mean, so when you impose a step sequence like this and ask actually what these state and rate related terms actually do. I mean, so specifically in a response to a step up, the amplitude of the friction change scales with actually the log of the step size, and a log of the step size is the amplitude of the friction change, and then as the speed is kept like constant at some post step speed like v2, the state evolution amplitude is given by this p log of the step size. Now, of course, to specifically like understand the state evolutionary details, one needs to specify a state evolution equation, and the two standard versions of this are the aging law and the slip law. So the aging law actually states that the rate of state evolution can actually be expressed in a form like this, where when this quantity like v theta pi like dc is equal to 1, the sliding interface is actually at steady state. And importantly, what this also states is that when the sliding speed drops down to extremely small values, then the state can still change as a function of time. So state can evolve in this picture as purely a function of time, even in the absence of slip. But on the other hand, you have the slip law, which actually states that the steady state of dependence is still the v theta prior DC equal to 1, but when the speed drops to extremely small values with respect to the steady state of theta and the d sub c length scale, then the speed of change of state or the rate of change of state itself will actually drop to 0. So in this case, what you have is that the state cannot evolve unless you have some actual slip on the interface. Now, what these state rate equations imply in terms of the transition in between aseismic and your seismic slip is this, that in case you are driving a sample with a spring of like stiffness K, and the sample has a specifically B minus A value. So this quantity, this sigma effective times your B minus A priorly D sub C has the dimensions of a stiffness and is actually called the critical stiffness. So for a specifically testing assembly which has a stiffness K smaller than this Kc, the critical stiffness, in response to any small perturbation of the slip rate from a steady sliding in a block, the block would actually go unstable and undergo seismic slip. But so on a plot like this, on the x-axis, now you have the load point displacement, and on the y-axis you have actually the shear stress or the friction. So in these experiments, what you actually see is that as you continually decrease the sigma, which is the same as decreasing this quantity here, and hence the K by KC ratio, you transition from stick slip, which actually looks like standard earthquakes at high normal stresses, all the way to slow aseismic slip at the small normal stresses. I mean, so what this shows is that the strain rate equations have inbuilt in them the ability to specifically show the transition from unstable seismic slip at high normal stresses to stable aseismic slip at small normal stresses. Now, if so, as long as, of course, inside a sample, V is small. V is smaller than A, so that sample will always be completely stable. So in terms of essentially the subduction zone, experiments have actually been done in the laboratory to study how this A minus B quantitative changes with porthallic temperature and with the ambient stress level. So what is seen in these experiments is that only in a specific temperature range is A minus B actually smaller than 0. So in case one thinks of a subducting slab, then only in the zone here in the pink is A minus B smaller than 0, and hence you have seismic slip. But in the down-dip region from this unstable region, you have the conditionally stable region where A minus B is extremely close to 0, and then this stuff in the blue where A minus B is actually positive, and hence you only have stable creep. So this understanding of the state rate equations and the stability of faults can explain actually why the specific depth distribution of earthquakes on a transform fault here, like the San Andreas fault, actually would be expected to have a peak at approximately the 5 and 10 kilometers. Now, in terms of like geological characteristics, so this is a specific example from the Sakali fault in southern Italy. So in panel A, you have actually a zoomed in view of the structure of the fault zone. So the structure is spatially dominated by these highly foliated stone rich in clays phyllosilicates, and then in this broader structure are embedded these carbonate and graphic lenses. So in experiments which were done in the lab by Cristiano Colatini et al., what was actually seen is that in case you took samples from the clay around the lenses, then A turned out to be substantially larger than the B. But if you took samples from inside the lenses, then A specifically turned out to be so then A turned out to be like smaller than B. So any slip perturbation inside this clay-dominated region would only like lead to slow aseismic slip, while the same speed perturbations inside the mafic lenses could actually lead to unstable seismic slip. So then in terms of the specifically geological context as well, the state rate equations hand us a specifically mathematical structure of framework through which to understand that how specifically geological heterogeneities can actually lead to the transition in between the seismic and aseismic slip. And then just this one important slide in terms of the observations that in case we draw actually depth distribution of earthquakes in the brown here and slow slip events in the blue. So these observations are from the subduction margins actually in Japan. So you see that all of the aseismic events happen at the same depths where the P2 S wave ratio is specifically the maximum. So higher P2 S wave speed ratios imply high ambient pore fluid pressures, and so this also shows that at the depths where you specifically seem to have high pore fluid pressures are also the depths where you have this aseismic and slow slip event. So in general, the framework of these state rate friction laws can explain the geological context within which the spectrum of the slip modes we actually observe along the major trade boundaries on the Earth can actually be explained. So, how much time do I have left? Sorry, so I did not keep track of time at all.
No, it's already 1 hour. You have you are speaking for 1 hour. But if you want, you can take more.
Okay,
no.
Well, I mean,
if you want.
Yeah, 5 minutes more, maybe. Just 5 minutes more.
Oh, yeah, sure.
Yes, okay. Yeah, I'm sorry about this.
No, it's okay. It's okay. Please go ahead. It is interesting. Please go ahead.
Yeah, okay. Okay, so now, so the other like checkpoint which we so I mean up till now I have been, I hope, able to like convince you that that even in terms of like simple dry frictional system, these state rate equations can specifically be used to understand the transition in between aseismic and geoseismic events, right? So, but in the same like checkpoint, I had also specifically mentioned that that any constitutive friction law of actual faults will also have to be able to explain the observation that on the vast majority of crustal faults in the earth, we seem to observe earthquake cycles, which implies that after the occurrence of one earthquake on a fault, the fault will actually have to start to strengthen in order for it to be strong enough to allow enough strain accumulation in order for the next earthquake to happen. So in all this while, I have not at all spoken about how the state rate equations can explain this strengthening of faults. So to understand that, we have to now sort of like shift our focus from the speed or velocity step experiments to a second class of experiments called slide hole slides. So in these experiments, what is actually done is that the system is continuously loaded at some steady background rate, and then this sliding rate is then dropped completely to zero, and so the friction coefficient of the fault, which is essentially the shear traction divided by the normal traction, can start to essentially go down all the way till the driving is started back up once again. And as the driving is started once again, the shear stress or the friction comes up all the way back up to a peak, and then once again comes back to steady state. So the interesting observation from experiments of this style in the lab, where this time span of the whole duration is increased logarithmically, is that this peak strength of the sliding interface increases approximately like linearly as a function of the log of the whole duration. And in case you come back to this observation of how the seismic stress drop also increases as a function of the earthquake time recurrence intervals, one interesting observation is that this increase in the stress drops is also approximately like linear across time in logarithm, right? I mean, so the specifically phenomenology of the strengthening of the frictional interfaces at small sliding rates seems to be extremely similar to how crustal faults actually strengthen over time. And what's interesting is that even the state rate equations have this thing inbuilt in them. So in both the aging and the slip law, in case you impose a step down in the sliding rate, so instantaneously what you have is that this quantity, the speed times the state scaled by the d sub c, is instantaneously actually smaller than 1. So as soon as this quantity is smaller than 1, this state will the state rate is instantaneously larger than 0, and as long as the interface is below steady state, so this quantity is smaller than 1, state will keep on increasing. And these experiments of holes are essentially extreme velocity step decreases, right? I mean, so then across a hole like this, as this quantity drops to values much smaller than 1, state keeps on increasing, and it can essentially be shown that this quantity, the change in the friction of the peak, this quantity scales with the change in specifically the log theta across the duration of the hold. So then anytime that the sliding interface is sliding extremely slowly, the state quantity will start to increase, and the aging law specifically said that this increase in state scales with essentially the log of the time of the hold, while the slip law says that the increase in state scales with the amount of slip in the course of the hold. So one interesting experiment which has been done on this is to try to do the same sequence of holes. Is to try to do the same sequence of holes on two extremely different stiffness machines, and the observation from this is that in the squares you have essentially the peak strength as a function of the log of the whole time, and you see that the rate at which the strength increases in terms of the whole time seems to be independent of the machine stiffness. So this is something which is captured by the aging law, but not actually the slip law. And with that, I think that I'll stop. I think that I've been able to show that these standard and laboratory derived laws contain all the ingredients that we need in order to explain the whole spectrum of slip phenomenology on crustal scale faults. If time permits, the next time I would actually love to speak about what is specifically the physics which can be used to understand the processes underlying stage evolution, but it should amaze us all that that even experiments like done on small centimeters scale examples in the lab can provide like such a self-consistent like framework within which we can understand the mechanics of crustal scale faults, and in case I'm invited second time to speak, I would absolutely love to speak about the physics behind these laws. And with that, I thank you all.